And we define what's called an optic axis. And the only reason I'm dwelling on this is because last year the students kept asking me what this meant. So an optic axis, you typically take an optical element like a camera lens. It's perpendicular to it and goes right through the center. So it's just be common sense. You got this lens system. You're going right down the center of symmetry of this thing. That's the optic axis. We define a ray with respect to the optic axis, and the key issues were its height and its slope. Now, I got thinking about this too. I'm using the letter R as in radius, but typically, if I'm down here, this is going to be a negative, and this is a positive. So I probably should use X and X prime, or Y and Y prime. We use R, I don't know why. If you have a symmetric system, then it's radially invariant. Doesn't matter if you're X or Y, it's the same issue. If you have non-uniform X and Y, if you have an asymmetric lens, then you would have an X and a Y vector, and you'd have a 4-column vector. And I've seen these things, X prime, Y prime. In general, we're just going to deal with perfectly circular ones. And so we just have one variable. But don't think of it as a radius, because if I'm down here, this would be a minus value, and that'd be a positive. So my slope can be, if it's going away from the axis, it's positive. If it's going toward the axis, it's negative. If it's down here, other way around. So think in terms of that. Think in terms of X more than that. So that's we talked about. Our goal in ray tracing was to develop a series of expressions where we could define how a ray propagates. And we did it in terms of these things called the ABCD matrix. So if I know a ray at one point, I try to define my optical system in terms of these ray matrices, and then I know the ray at the subsequent point. And so we build this calculus out of ABCD. And this is very common. If you look at a classic text on lens design, it's ABCD. Now this was taken from lens design, nothing invented here, but it's a classic way to do these things. The other issue was we talked about the Paraxial Approximation. And in that, we're going to assume that the slopes are usually less than 15 degrees. Effectively, what we're saying is tangent theta equals theta. So we get rid of all the sines and cosines and that kind of stuff. So a paraxial approximation means the ray is pretty much along the axis. In lasers, this is almost always the case. It's very rare you get a beam diffraction more than a few degrees. With a tight focusing lens, you might exceed it. It turns out it's a very non-impactful approximation. So we don't see any penalty from this. So it's a nice approximation. What it does is it eliminates our ability to calculate things like astigmatism, coma, and some of the classic optical parameters you look at in distortion. Well, we're not worried about that anyway. We're just trying to get our beams moving around. So distortion is not an issue, and so we're not going to worry about that. But anyway, so we'll use that, and we'll use it in Snell's law. It lets us get rid of the sine theta, replace with theta, and things are a lot easier there. So we did some examples. We developed some ABCD matrices. One was for propagation, going from, say, Z1 to Z2, and this is a distance L. We found the matrix for this, if you recall, was simply 1L01. So if I have a ray here, and I want to know what the ray is going to look like when it gets down here, I just operate it on 1L01, and that gives me my new position and slope. And then we looked at the lens, and we found that if we have a ray entering the lens and a ray leaving the lens, it is defined in terms of 1, 0, minus 1 over F1. And that was ABCD for that. So what I want to do today is we're going to develop two more, and then we'll look at a system. And so once we've gone through a couple more examples, you should be able to develop an ABCD matrix from anything, because it is just a matter of just playing around, just sitting there and fooling around a bit. So we're going to try a curved mirror, because those are used a lot in lasers, and we do a dielectric interface. And then I'll let you combine a curved dielectric interface and all that kind of junk and learn from there. So that's the goal today. So let's look at a curved mirror. This is a very common element in lasers. Lasers always have mirrors on the end. Usually they're curved. So the curved mirror is used a lot more than, say, lenses are. So we've got this curved optic like that. And it's a reflecting surface. We define an optic axis through the middle of it. And you define a curved surface by its radius of curvature. So when I buy a mirror, I'll say I want to get a 50 centimeter radius curvature or a 25 centimeter, I'll define what the radius is. And so it'll come with its curvature, and it's just a perfect sphere. And that's part of the specification. So a lens, I'll say I want a focal length of f. A curved mirror, I'll say I want a curvature of r. So what's the ABCD for this? So again, we're going to play and just kind of take some rays we can kind of think we know what's going to happen and play with them. So simplest one here, let's bring in a parallel ray. Let's just say we come in like this and hit that surface. Now this is a curved surface, but we look at it microscopically. So we zoom in real close, and here's this ray coming in, and we treat it like a locally flat spot. And so if it's locally flat, here's the radius, it comes in an angle theta, it's going to leave with that same angle theta. So we get equal angle reflection. So I know that whatever this angle is here, it's going to leave with that angle there. So what's this angle? Well, okay, so if I've got a ray and it's coming with a height r and a slope of 0, I know it's hitting the mirror here at a position r, and I know that this distance here, this normal, is a distance r away. So this angle here, theta, is just equal to r over capital R. Actually, it's going to be I guess the sine of theta is going to be little r over hypotenuse. Sine of theta equals theta. So that's where the paraxial approximation comes in. So here's my slope, r over r. Buy that? So I know this angle, and so when it reflects down, it's going to bounce down like that. So now I know the exit angle. Okay, so what I'm going to try and do now, I've got to figure out what R2 is, and that's equal to A R1 plus B R1 prime, and R2 prime is going to C R1 plus D R1 prime. So we're going to try and fit these things together. So we can, a lot of this we can do by inspection. So I'm going to come in, this ray hits this mirror and bounces. What is R2 compared to R1? Does R2 change from R1? No, it always is going to be the same. So I can just look at that and say, you know, there's no doubt in my mind that A equals 1. You know, this is always going to equal R1. What if I come in at an angle? You know, what if I, instead of parallel, I come in like this or like that? You know, whatever I come in at, does the angle of incidence matter on where R2 is? No, because it's all happening at this one surface. You know, here it bounces. I come in like this, it bounces. I come in like that, it bounces. It always enters and leaves at the same point. So I can say, you know, the R2 does not depend at all on the incident angle. So this one is, you know, pretty easy to say. I just, well, this is going to be plus 0 times R1 prime. I can just do that without any formulas or anything. I'm just looking at it. Does that make sense? So a lot of these ABCDs, you just look at it and kind of, okay, makes sense. So I've already got A and B. Now let's look at this thing here. I came in at height R. I'm leaving at that. What's that angle? Well, it's theta and theta. It's actually going that way. And so it's leaving at an angle of 2 times that. Okay, so my exit angle is different, and it depends on R1. Okay, so what's the value? So what's C? I'll give you, yeah, there's R1. So it's twice that angle, right? Now, is it a positive or negative angle? This is a tricky question. So I came in like this, heading down like that. Is that a positive or negative angle? It's a negative angle. What you do here, you might say, well, look, it's pointing up like that. So this would be positive, that's negative. No. Ride with the ray. So the ray is coming along, it bounces, it's heading down into the optic axis. So the ray has changed direction, it's heading into the optic axis, so it's a negative angle. The angle is twice theta. Theta is R1 over R. So the exit angle is 2R over capital R, and it's negative. So it equals minus 2 over capital R, R1. That make sense? They're just playing around, So we got that. So now we've got A, B, and C. We don't know D because we came in with a slope of 0. And so whatever we put here, we're multiplying by 0. We can't derive it. So we're partway there. You always have to come in with a second ray. So we have to come up with another ray which we can kind of predict what's going to happen. And so this one, to me, what I'll do, I'll say, let's just launch a ray from here. I'm going to launch a ray up, bang, and it's going to come back. So my test ray is going to hit at a height of R, and it's going to have an angle, a slope of R over R. That's R1. What's R2? It's going to morph into something which has the same height, but it's coming down with minus R over R. All right, so it goes up like this, it bounces, just comes right back down. So I know my entering and exit ray. I just did that by looking at it. And now all I have to do is fit it to that equation. So since we know A, B, and C, we can just plug this in. So I know that R2 prime is going to be R over R. It's going to be negative. That's equal to C, which is minus 2R over R, plus D times my input slope, which is R over R. Okay, one equation, one unknown. Solve for that. Clearly the answer is D equals 1. And so if I do that, I now find that my ABCD for the curved mirror is it's 1, 0, minus 2 over R, and 1. And that is, in fact, the ABCD matrix for a curved mirror. Now compare that to a lens. Notice they look about the same. And here I've got 1 over the focal length. So here a curved mirror behaves just like a lens. It's focusing, and the effective focal length is 2 over R. Or, I'm sorry, it's R over 2. This is 1 over F there. So the effective focal length is R over 2. So if I have a 50 millimeter focal length lens, I would have the same focusing power if I took a 100 millimeter curvature mirror and bounced off that. That would focus the same way. So they're both focusing elements. That's the power. Yeah.
Why are we saying that B is definitively 0? Because R1 prime is also 0. So could B be the angle?
Well, in this case, R1 prime was 0. But in this case, R1 prime is I've came in with a second ray.
I'm saying for the R2 case, not R2 prime.
Oh, R2. Oh, yeah. Why is this 0?
Yeah, because R1 prime is 0, so could B really be any value?
Yes, yeah. Mathematically, I didn't prove it.
Okay.
I just said it's obvious, right? So, but and I just looked at it in a cartoon fashion. I've got this mirror here, and no matter how I come into this thing, I'm always going to bounce, whether I'm parallel or slope, I'm always going to bounce at the same point. So my height doesn't change on reflection. It hits and bounces, always going to bounce from that same point. So R stays fixed. I could have left that unknown. I could have left this as I don't know what it is. And then we come in with our second ray here. And so I got R equals R. And so now I've got R equals 1R plus, what's my slope? My slope is R over R times B. So that would be the mathematical way to do it. And then, of course, B equals 0. Yeah, so you can always derive these things. So you've got two equations. You just set up two rays. It gives you 4 conditions and 4 unknowns. So that's a good point. Anything works. Now, one thing I want to make clear is that this matrix, let's look at the lens. The matrix only describes what happens at the lens. So, I've got this lens here. I'm effectively treating it as a thin lens, and a ray is coming in and it's leaving. And this matrix connects this point to this point. And this is delta getting small. It only tells you exactly what happens to the ray right there. It doesn't subsequently focus it. We've been bringing rays in and bouncing them, and they come off and come to here and so forth. And that's true. But as far as ABCD is concerned, that lens matrix up there describes a ray going from here to here, just crossing that lens. It came in and something happened. And all we did is change the slope, basically. And now we have to subsequently propagate it. Same thing in the curved mirror. This matrix describes what happens between, as the ray comes in and leaves. The ray comes in and changes right there. But it hasn't moved an inch. It hasn't moved a nanometer. It's just right there. Suddenly the ray changes, and then we subsequently have to propagate it along. So this matrix is only valid for that one point. And so you say, well, God, we got a finite thickness here. We assume everything is thin, and so we don't worry about that difference in propagation length. And usually that doesn't cause a problem at all. So we won't worry about that. I don't know if you got a homework on a thick lens. I haven't looked at your homework. Do you have a thick lens homework? All right, I'll give you one. So I'll let you do a thick lens. So I'll have you calculate what happens when your lens looks like this. So I've got one radius here, another radius here, and a big chunk of glass in between. And you can describe this totally as an ABCD, and then you'll find as you let t go to 0, it boils down into this expression. So the thin lens approximation is an approximation, and you use it rationally. If you really have a big thick lens, use a thick lens approximation. But this matrix takes you from the entrance to the exit of that device. Let's do one more, kind of to give you a tool, and that would be the dielectric interface. Then once you've got that, you've got all the ammunition you need to create any sort of ABCD. Not that you could figure this out on your own as well, but let's imagine I've got a dielectric. So here's air, and here's some glass. Here's the optic axis. And we're going to come in with a ray, and I want to take the ABCD across that interface. So what's going to happen? So you have to say, okay, well, what's physically going to happen? So physically what's going to happen is Snell's law. The ray is going to refract. So we define our normal. We have theta incident and theta exit, theta 2, let's call it. Snell's law would be n1 sine theta 1 equals n2 sine theta 2. So 1 sine theta 1 equals n sine theta 2. That's Snell's law. In the Paraxial approximation, this becomes theta 1 equals n theta 2. So we get rid of that pesky sign. And so that's the whole physics of this thing. So now we just bring in some rays. So this one, I don't even know what, a test ray doesn't do much good. Let's come in with some angle. We just choose an angle theta. We know what the exit ray is. So if I come in with a high R and R prime equals theta 1. So theta 2 is going to equal theta 1 over n, or R prime over n. So this is going to morph into R prime over n. So that's what's going to happen as I cross that interface. Nothing more. So what's the matrix for this? So again, I'm going to kind of just wing it here. I want to find ABCD. So R2 equals A, R1 plus B, R1 prime, R2 prime equals C, R1 plus D, R1 prime. Okay, the height doesn't change at all, so A must equal 1. How about B? Since the ray, the height doesn't change at all, depending on where I come at, no matter what the slope is, B is equal to 0 again. So this is 0. Does this is a planar surface, so does this refraction depend on where I hit it? So if I let R go from -10 to +6 or whatever, does my refracting angle change? Here's my refracted angle. And I hope you say no, it's independent of position. It really doesn't care. This slope is going to be the slope no matter where I hit, so long as I come in with the same slope. It only depends on my entrance slope. So C is going to be 0. And I say, well, my exit angle is my entrance angle divided by n. So here's my entrance angle, so D is going to be 1 over n. So my matrix here is 1, 0, 0, 1 over n. And of course, if this was n1 and n2, then it'd be the ratio of n1 over n2. But that's the basic idea there. So the only thing that's happened is I've changed my slope on the exit and nothing else. So that's the dielectric interface. Now you're ready to go. If I gave you, now you could sit down and calculate what a lens looks like. If I give you a piece of glass like this, and it's got an N and this is air, you can now derive this matrix. You should be able to do this. Come in with a ray, figure out what happens when it crosses that interface. You got to figure out the local angle of incidence it's hitting at, apply Snell's law around that local angle, and then figure out the exiting position, and you get it. So you can now do that. That'd be a fun thing to try, just to practice these things. But now you're ready to go. All right? So that's all there is to ABCD. You can derive these things all day long. Let me say one last thing about it. And this is a good check. When you build a cavity and you do all these sorts of stuff, you usually want to check to see if you made a mistake. And in general, this is true. The determinant of the ABCD is equal to 1. And you're going to look at this and say, no, it's not. So we'll talk about this in a second, okay? Ignore that. But here's this one. AD minus BC is 1. AD minus BC is 1. Whenever I enter and leave in the same index of refraction, the matrix, the determinant is 1. What's that all about? That actually has a reason. This comes from something called Louisville's theorem, which I'm not going to ever hold you for. I'm just adding a useful fact to excite your day. This is classic optics. And if you look at a beam of light, it has a finite diameter and it's got a certain angle it's spreading at. There's a conservation between the size of the beam and its spreading angle. And if I focus it, I can make it tight, I can really increase the diffraction angle, but I make a smaller spot. And there's kind of an uncertainty relation between the size of the spot and the diffraction angle. So writing this in phase space, if you want, you can write, let's say this is x and this is theta for a beam. And let's say I've got a very big beam and it's collimated. So it's quite large, but it has very little, how do I do this? It's large, yeah. So it has very little diffraction angle. So it extends over a large area, but it's not spreading very much. So this would represent just a big beam. Here's X cruising along towards you, and it's not spreading. So theta is very small. Now I slam it into a lens and focus it down tight. What happens is now it focuses down to a very tiny area. So X collapses, but my angles increase. And so after going through this lens, it looks like this. So this is the beam, and here's the focus. And Louisville's theorem says the area is the same on these curves. So as I trade beam size for diffraction angle, it's always constant. The basic idea is you cannot make light brighter than it fundamentally is. Brightness is the number of photons per sterad, per solid angle, per area. And so if I increase the sterads, I have to decrease the area, and so forth. There's kind of a conservation of light flux here. That's where this comes from. This falls out of Louisville's theorem. If you look at A corresponds basically to magnification. D corresponds to collimation. B corresponds to focusing, and I forgot what C corresponds to. But if you magnify and collimate and focus and defocus and so forth, that product basically comes out to be 1. So that's where this comes from. You can forget all of that. You'll never be tested on this. It's just if you ever wonder why. But the key thing to remember is the determinant of your ABCD matrix is 1. And that includes when I've done, I've gone through lenses and mirrors and bounced off things and propagated and all sorts of stuff. That whole ABCD matrix, the product of that is 1, the determinant. That's how you check it. So it's a good test. And it just has to do with this conservation of brightness. Okay, what about this thing? So I go and say this, and here's this case here. So this is only true so long as you begin and end in the same index. So you have to stay in the same index. So either you begin in air and you end in air, or you start in the middle of your laser crystal and you come back and end in the middle of that crystal. So long as you're starting and stopping in the same index, this will always be the case. What's happening here? So here we're violating this. So in principle, we make things brighter if we have to. Have any of you worked with microscopy? You done an immersion microscope? You ever heard that term? So in microscopy, you're trying to see little tiny things, and fundamentally there's a thing called the Abbe limit, where you can see things to about half a wavelength. That's about the best you can do. And so one way you can beat that limit is by putting an oil index over your sample. And so if you've got here's this little bug you're looking at or something like that, and here's your lens, your microscope. Here you have air, and so the best you can do is kind of come in like that, and that gives you a half wavelength if you really have a good lens. If you fill this with oil, you effectively change the wavelength. You make it shorter, and so you can see things smaller. You have better resolution in an immersion index. You've effectively made the source brighter, if you will. And so that's where you're kind of defeating. You're starting one index, ending in another in air, and so you can boost the resolution. So you think things called immersion microscopes is playing that game. So that violates this. So if I have immersion, if I start in a different index, I'm not going to satisfy this. But if I start in the same index, I do. So keep this in mind. When you do your cavity designs, you run it through, always just check the determinant at the end. Just make sure you didn't screw something up. And if it's not 1, you screwed something up. Often you started it in the glass and you ended in the air or something dumb like that. So it's a good check. So we'll do some practice on that as we go. All right, let's look at some systems now. So the classic would be a lens system. I got a compound lens. Here's f1, here's f2. I got some distance between them. So I'd like to know how this operates on rays. So what I'm going to do is define an ABCD matrix which takes me from this plane here to this plane here. And now whatever ray I have here, I can now tell what it is over here. And so I build this thing by saying, okay, I'm going to write the ABCD matrix for each operation. First I hit lens 1. So that's going to be a 1, 0, minus 1 over f1, 1. Then I'm going to propagate a distance L. So 1, L, 0, 1. And then I'm going to go through another lens, f2. And that's going to be 1, 0, minus 1 over f2, 1. So I do the product of that, and I'll try and do that. It's going to be a mess, but that's going to give me an ABCD matrix which relates that surface to that surface. So again, after doing all this, so let's just do it. We're going to get a, let's say a 1. Let's just do the 1. I can't do this stuff. 1, crap. This is 1 minus L over F, 0 L, 0, 1 minus 1 over F, 1, 1. I multiply that one, so I go 1 minus 0. So I'm going to have 1 minus L over F1. L. Okay. This one's a mess. Minus 1 over F2 times 1 minus L over F1. And then minus 1 over F1. And then finally, God, L over F1 or F2. I'm just whipping through this thing. Plus 1. Okay, so there's my, that's probably, I probably made a mistake someplace. Okay, but I do this, I get a 2 by 2 matrix, and that is now the ABCD going from here to here. And it's, again, here's A, here's B, here's C, here's D. I'll put numbers in, I'm just going to get a number, 0.6, whatever. It's a big messy formula, but it describes it entirely. And what it does, I come in with some ray here, I hit at some angle and some position, and it leaves over here, and it's got some new angle and position. And it's totally described by this thing here. So I don't know what's inside that box, but it takes me from one point to the other. So that's the power of the ABCD. I can replace any sort of complex system with a simple 2 by 2 matrix, and it'll perfectly describe how the rays travel. And notice it takes me from there to there. If I want to go beyond that, I then have to multiply by another matrix. Notice the order of the multiplication. I first hit this one, there. Then I hit this one, and that's on this side. Then I hit that one. So you always kind of, you put your matrices down in the reverse order you went and grind them through. And that takes you there. Now what can I do with this? Well, let's say you got this thing, and so what's the effective focal length of that thing? So I've got this compound lens. I don't even know if it's going to focus. I don't know. How could I figure out what's the focal length of that system there? So you're handed this thing here, and they want you to compute the focal length. How would you do it? Do you remember the operational? What's the key indication of a focal length? How do you, if I hand you a lens, how would you measure the focal length? Do what? Yeah, yeah. You find some distant light, and you kind of make an image of it. Sunlight, burn an ant, that kind of thing. You figure out, take parallel rays and see where they come to a focus. So I'd look at this, and I'm going to come in with some parallel rays, and here's my system, and I'm going to see where it comes to a focus. How do I determine where it comes to a focus? Yeah, so I'll come in with some ray, say I'll call it R1, 0. I'm going to come in with a parallel ray. That'll be my entrance. What's my exit? I'm going to look for the place where this equals, where this point here, where I'm going to call it R3, equals 0. You'll have some slope. So that's one way to do it. To do that, what I've got to do now is take my ray and I've got to propagate beyond it. So I've got to go some distance 1. I'd have to go some distance here, and that distance is going to be F, or F effective. This matrix only gets me to here. So what I have to do is take this matrix ABCD, operate again. I have to go some distance 1, F effective, 0, 1. That's going to get me from here to there, and then I'm going to adjust. I'm going to look for where F effective. I'm going to adjust F effective to the point where R2 equals R3 equals 0. So that'd be one way to do it. So I come in with this. I go through this new matrix. I solve for R3 in terms of all that stuff, and I just adjust F until R3 equals 0. That would help me find it. That'd be one way. Well, another way would be if I know the height here, I know I can figure out the slope, and so I can just say, I don't care what the position is here, but I want to find a slope with respect to this. So if the slope, whatever the slope is here, my focal length, if this is R prime, here's R, my focal length, what's it going to be? It's going to be, I got to do my inverse stuff. This is R, that's R prime, so the hypotenuse, it's going to be, jeez, I can't think, R over R prime, is that going to be this distance here, X? So I can compute my position, my slope on the exit point here, and then use some trig and do it properly, not like me, and then you can figure out where it's going to cross the axis down here. But that's a way to use these matrices to actually compute something useful. You know, what is the effective focal length? And then you can say, oh, you'll get a focal length in terms of L. You can see how does it vary as I move L and so forth. Yeah?
That center matrix is for the rays traveling through space, right?
This one here?
No, I'm sorry, above that?
Above? Yeah.
So why is the B coefficient L and not 0?
I'm sorry?
Why is the B coefficient L and not 0? So you have 1 L, 0, 1. Why is that B not?
When I propagate, this is the propagation matrix for propagation. So I'm traveling a distance z, I get that matrix. So what we did first, we hit the first lens. Here's our lens matrix 1. Then we propagated, and we went a distance L, and then we hit another focusing. So I'm careful. I'm trying to put down the matrix for each operation. Does that make sense?
Yeah.
Okay. Yeah. So these get messy. I mean, the first laser I actually built, it was what did it look like? It looked like this. It's kind of fun. So it wasn't pretty simple laser by today's standards, but I had 1, 2, 3, 4 matrices. I had to multiply 4 matrices. It took 3 pages of a notebook because you do it all by hand with pencil, 2 by 2s, 2 by 2, calculating it out. Trying to figure, and I was trying to figure out what's the spot size here and here. So I was doing a couple of variations, but it took me most of the day just putzing around. And of course, you immediately check the determinant. Did I do it right or wrong? It was painful beyond belief. Now, of course, that takes about, 30 microseconds on the computer. So when you're doing these homeworks, I really suggest you start building up some code. Just have a little code in Mathematica or MATLAB, whatever you use. Have your matrices there. Just grab them, put them together. You could put together a 20-element cavity. Bang, you get the ABCD right away. From that, you can convert what's the spot size. It's a magic what you can do with computers now. They were made for laser design. But it's just an issue of taking these simple 2 by 2s, putting them in the right order, and marching along. What we'll find, let's say I want to know where the spot size is right there. I will start my ABCD right there. I'll propagate, focus, propagate, focus, propagate. So you do 4 or 5, but it's trivial with a computer. So really practice that when you're doing your homework. Start building up this library and get used to doing matrix multiplications and computing things. So you have to know which, the key thing is put the right matrix in at the right time. Any questions on that? Okay, it's pretty simple. Well, you have a homework, right? Have you looked at the problems? Do they have any ABCDs?
Yes.
Okay, I need to look at that. What does it do?
We take the results from 2 different lens configurations and then we use it to find one for the third configuration.
So it's this.
Yeah.
Okay. Are you doing a thick lens? Okay. I'll throw a thick lens problem on there just for your joy. Everyone should do that. Anyway, so this is, the ABC is pretty simple stuff. And it really is, it's just nothing but rays, which seems kind of odd. And we're going to use that for determining what Gaussian beams look like and so forth. But it's a very powerful tool for doing all this stuff. So you must know how to use these elements. So absolutely know the lens, know the curved mirror, wherever that was, know transmission, and know the indices. In this laser here, typically the laser you're going to design, you're going to have a crystal. And you probably want to start in the crystal. You want to propagate. You're going to hit a dielectric interface. You're going to have to do that dielectric thing and leave and propagate and so forth. Let me ask you a trick question now. What's the ABCD matrix for this? So let's say I've got a laser and I want to tune it with a prism. So I've got my cavity. I can put a prism in here. I'll put my mirror there. So I'm going to tune it. So I've got, let's say, a curved mirror here. I've got a curved mirror, a distance, a prism, a distance, another mirror. I'll make it a flat mirror there. So there's my cavity. So we know the ABCD here. This is pretty easy. This is just 1, 0, minus 2 over R, 1. I know this distance. So this is just going to be my distance matrix. How would I do a prism? Any thoughts on that? Yeah.
2 lenses.
2 lenses? Does it focus? It's a trick question. It's evil. Yeah.
It's just 2 dielectric interfaces.
Yeah. Maybe. So, what's nasty about this, where's the optic axis? Because we always define our ray with respect to the optic axis. And so, effectively, here, what I've drawn is actually the optic axis. And the ray is going to basically track that optic axis. So the prism has no ABCD matrix. It doesn't alter the rays with respect to the optic axis on propagation. It changes depending on the wavelength. So if the wavelength changes, the angle changes, but so does the optic axis. So this is a really, really nasty question. I put it on a prelim once, really ticked off the class. So the rays are always defined with respect to the optic axis. And in this case, I mean, it has a very subtle impact of the interface, but it's so subtle we wouldn't worry about it. So this has a matrix of unity because it doesn't do anything. And so we go, here's L1, here's L2. How about a flat mirror? What's the matrix for a flat mirror? So I got a mirror, a ray comes in and bounces. What's the matrix there? So does the height change? No. Does the angle change? No. So nothing changes. So a flat mirror, you can think of it as having, it's got minus 2 over infinity for curvature, or it's just basically a unity matrix. So a flat mirror, it just reverses the direction but doesn't do anything to the ray. So everything about these things, these rays, you always think about how is the ray change with respect to my axis. If it hasn't changed with respect to the axis, if the slope didn't change or the height didn't change, it's a nothing event. And that's why the prism's kind of a nasty question. The ray does bend, but so does the optic axis, and they just track each other right on through and have no impact there. So, subtle question. You could, if you really want to be tricky, but you could say, well, I've gone through so many, millimeters of glass, and so you could add that as a dielectric interface if you want, in and out. But it's not going to change your answer very much. Okay. What else could I ask? I think that's about all I want to talk about today. Do you have any questions about this? Okay, so what we'll do is we're going to take this now and look at cavities and ray tracing. We're going to build a cavity and launch rays in there, and then look at how the rays propagate back and forth. And we're going to find that given how you put your mirrors together, you can either have the ray stably stay in the cavity, so the ray never leaves, or you can have the ray quickly get out of there. So this is called a stable cavity, and the other one is called the unstable cavity. And there are lasers which are built with stable versus unstable. There's applications for both. Most lasers you've seen use stable cavities. So this is a big criteria, is when you build a cavity, is it stable? And then once we get there, we'll figure out, okay, what is the size of this thing? How big is the beam inside there? And that gets us into the Gaussian mode and that kind of stuff. So that's what's coming up. And so I think I'll stop there. I'll be better prepared on Friday, and we'll continue on that. All right? When is your homework due? Do you know? Next week? Next Wednesday. Okay. All right. I don't want to overburden you, but.